This is video lecture 9.1 on atomic spectra and energy levels. All right, so in this lecture, we're going to look briefly at spectroscopy. We're going to look at how spectroscopy tells us about atomic emission. Well, we'll look at two kinds of spectroscopy, emission spectroscopy and absorption spectra, and then we'll see how that can be explained with the Bohr model or by looking at atomic energy levels. The Bohr model is kind of an early model. It's useful, but it's not exactly correct. So the more accurate way to do that is just to think of it in terms of atomic energy levels. And we'll look at the comparison between those two models. And then we'll also look at some transitions between different energy levels. All right. So we'd mentioned previously that spectroscopy is basically a discussion of how light is affected by its interaction with matter. And so when we look at um, light interacting with a substance, there are changes in the nature of the light before and after it interacts with that substance. And by looking at those changes, we can understand things about that material. Mhm. All right, so the first thing we want to look at is black body emission spectra. And this is the most common kind of emission spectra that you will see. This is the kind of light generally that's emitted from a hot object. If you stick a poker in the fire and you allow it to heat up in the coals and you pull it out, you'll see the poker is kind of glowing a dull red color. You can see this also with a blacksmith who's working a horseshoe or something like that, and he sticks it in the furnace and pulls it out, and the metal is glowing red or yellow or orange. That's black body emission. Uh, some other examples of black body emission are the sun, right? The sun's glowing because it's extremely hot, and so it also emits black body emission. Okay, so how you can recognize black body emission, this is this is a little drawing here. This is a light bulb. This would be an old-fashioned light bulb, say an incandescent light bulb, the kind of light bulb that I grew up with, which I guess now I'm saying is old-fashioned. Maybe that means I'm old-fashioned too. Um, and an old incandescent light bulb also is an example of black body emission. There's a little tiny tungsten filament inside there, and when a current goes through, that filament heats up, gets very hot, and it emits black body radiation. Okay, so the characteristic of black body radiation is that if you take the light that comes off of the object and put it through a prism, it will break that light up into its various colors, and you will see that the light contains all of the different colors. It contains a continuous spectrum. It's got red light, yellow, orange light, yellow, green, blue, so on and so forth. Okay. If you were to make a sketch that, if you were to graph the intensity, so let's say you had a graph here and you've got wavelength down here, and we'll graph intensity on the y-axis. What you'll find is there is a small amount of light with very short wavelengths, more light with longer wavelengths, and then this kind of tails out like that to longer wavelengths. But all of the wavelengths are included in this spectrum. So you can see this is what it looks like as a graph, and this is what the actual spectrum would look like. All right, now we want to compare that with the spectrum that you get from uh, hot atoms, right? If you heat atoms up to a high temperature. You can turn them into a plasma. The electrons are pulled off of the rest of the electron, and then when the electrons recombine, they emit light. But this is not light being emitted just because it's hot. It's light being emitted because of electrons moving around through different states in the atom. So a couple of examples of where you see this is neon lights. Neon lights are called neon lights because originally these tubes were filled with neon gas, but you can actually fill them with a lot of different gases. The noble gases in particular are good for this, but you can also make lamps like this from mercury vapor and sodium vapor. A few other things make really nice lights. Uh, this also explains the light that you see from fireworks. Um, all these different colors that you see are because these different fireworks contain different elements, and different elements are going to give you different colored light. And lasers also. You see lasers emitting light of a lot of different colors, and that's because they've got different things in them. This one down here, the one you see most often, including the lasers that you see in grocery stores that read your barcodes, those are helium and neon lasers. Those red lasers that you see all the time are almost always helium neon lasers. All right. Now the important difference between blackbody radiation and atomic emission spectra is, let's say you've got a sample, you've got some gas, you've got a bunch of atoms here in this gas sample. And you heat this up to make a plasma. The atoms and the electrons get separated, and then as the atoms and electrons come back together, um, the electrons move through different energy levels in the atom. And when that happens, it emits light. And if you take the light that's emitted from this hot gas sample and you put it through a prism, it will distribute out and give you a spectrum. But this is the important difference. For atomic emission, instead of getting all the colors, you only get a few specific colors. In this particular case, you're getting red, yellow, green, blue, and there's a little bit of purple down here. And when you separate them out into their specific colors, what you get are a bunch of different lines. And so this is often called, in contrast to a continuous spectrum, this is called, apologize for the handwriting. This is called a line spectrum. And we can make a graph of this too, just like we did for the continuous spectrum. If we plot wavelength on the x-axis and the intensity on the y-axis, what we see is that for most wavelengths, there's no light emitted at all. So the intensity is 0. Let me choose a different color here. The intensity is 0. But at a few specific wavelengths, a lot of light is emitted. So you get a high intensity at only a few specific wavelengths, and the intensity is 0 everywhere else. So if you plot this into a graph, that's what a line spectrum would look like. And pretty much all atoms, when you heat them up and they emit light, you're going to get some kind of a line spectrum. The position of all of these, position of all those different lines is going to be different for each atom. Here are a couple of example line spectra. This is a hydrogen, helium, neon, And sodium, you might notice sodium over here. Sodium has these really bright yellow lines in its spectrum. Sodium vapor has been used for a long time for street lamps, and you may have noticed um, street lamps very often have kind of a yellowish glow to them. And the reason for that is because they have this sodium vapor in them, and the sodium vapor is emitting these bright yellow lights at these specific wavelength around 590 nanometers. Gradually, sodium vapor lamps are being replaced with LED lights, because LED lights are a little bit more efficient, and the LED light that's emitted has a broader spectral range, so it doesn't look so yellow. It looks more white, and that's a little bit better for seeing at night. Because each element has its own specific pattern, uh, these line spectra are sometimes referred to as atomic fingerprints. And that's one of the ways we can analyze things to see what's in them. If we take something, dissolve it, and then take the solution and heat it up, we'll get lines that are emitted. And by looking at where the light is in the heated sample, we can tell what elements were in the original sample. All right. So that leads us to a bunch of questions. Um, why do atoms emit and absorb only specific colors? You saw the hydrogen, for example, only has four colors. I think there's a red, a blue, a green, and a purple. Um, emits only those specific colors and no others. Why is it that different atoms emit different colors? And how are these spectra related to the structure of the atoms? All right. So we're going to look at that with the Bohr model. That's what we'll look at next. All right. The Bohr model was proposed by physicist Niels Bohr. I think he was Danish in about 1913. And so this is a little model here that describes the Bohr model, little drawing. I like to use this drawing. I find it's helpful a lot. A lot of textbooks will not include this drawing. And the reason that they don't include it is because it's not really correct. The idea here is that the electron or the electrons are orbiting the nucleus in these little circular orbits. That's actually not how we currently understand the structure of an atom. And a lot of textbooks don't like to include this picture because it's very simple and it makes a lot of sense. And the textbook authors are afraid that some people will allow this to kind of become imprinted in them. And once they learn this, it'll be difficult for them to unlearn it, to understand the more sophisticated model of atomic structure after that. I don't think that's necessarily a problem. I think the Bohr model can be really useful, so I like to include it and I like to use it. You just have to be careful to remember that actually there is a better and more sophisticated model that came after this. All right, so what does the Bohr model say? The Bohr model, first of all, says that the electrons travel around the nucleus in circular orbits. Okay, we've already said that that's actually not true, but it's an early approximation that makes some of these calculations easier. All right, only specific orbits are allowed, and this is a really interesting idea. There was really no physical reason that this should be the case. If you just use classical physics, it should be the case that the electron can orbit the nucleus at any radius. It could be here or here or here or here or here or really anywhere at any distance from the nucleus should be possible. The Bohr model says that's not the case. It can only orbit at these specific distances. And there really wasn't any, like I said, there wasn't any reason for that. It's just that that was a kind of a strange, say maybe revolutionary assumption that you had to make in order to make sense out of those line spectra that we saw on the previous page. All right, so electrons travel in circular orbits, only specific orbits are allowed, and the energy of an electron in the orbit is given by negative RH. RH is the Rydberg constant, specifically with the H on it, the Rydberg constant for hydrogen. All right. So each one of these orbits, we'll call this orbit number 1, orbit number 2, orbit number 3, 4, 5, and those extend on and on outward 7, 8, 9, 10, in theory up to, well, I guess you could say in theory up to infinity, but that n can be any number. Okay, so this E sub n means the energy of an electron in orbit number n. And then this is equal to negative RH, that's the Rydberg constant. Let me write that down over here. The Rydberg constant is 2.18 times 10 to the negative 18 joules. Okay. Again, since that's a constant, that should be on your exams. And if you are looking for that number and you don't see it, then you can ask for it. Okay, I'll always give you the values of constants. Okay. So it's that times, I'm going to write this two different ways, z squared over n squared, okay, where z is the charge of the nucleus. So this is z here. And n, again, n is the number of the orbits. Okay. All right. Now you can also write this, you'll see this written a couple of different ways. I'm going to change this. And z squared over n squared is mathematically the same as z over n squared. All right. So sometimes you'll see it written one way, sometimes you'll see it written the other way. Mathematically, they both mean the same thing. All right. And the light is emitted when an electron moves between two different allowed orbits. And the energy of the photon that's emitted is just the difference in energy between the initial state and the final state. So basically, what the Bohr model is saying, let's use blue here, is let's say you have an electron out here in orbit number 4, and it drops down into orbit number 1. Okay. As that electron drops down to a lower orbit, its energy decreases, and so there is some surplus energy, and that energy is given off as a photon. And chemists typically use H nu as the symbol for a photon. Okay. This is an example of a relaxation or a decrease in energy. which results in emitting a photon. You can also have the reverse procedure, where an electron is initially in a, oops, get my pen back. Electron is in a lower energy orbit. A photon comes in bringing energy, and then the electron is excited into a higher level. Okay? In that case, since the electron is increasing its energy, a photon has to be absorbed rather than emitted. Okay. All right, and let me add one more thing here, in case this was not in one of the, this is part of chapter 8. Need to remind you of this in the chapter 9 videos, and that is the energy of the photon. Well, here we have over here, the energy of the photon is just the absolute value of the change in energy. The reason I've got absolute value there is because if the electron is going from a high energy to a low energy, that change in energy is going to be negative. If it's going from low energy to high energy, the change in energy for that electron is going to be positive. So delta E can be either positive or negative, but the energy of the photon is always going to be positive because the energy of the photon is just the amount of energy. Okay. All right, so I want to remind you also that the energy of the photon is Planck's constant times the frequency. Okay. All right, so let's look at this the Bohr model. All right, so the Bohr model, one of the things that we found early on is that the Bohr model only works well for electrons with one atom. So a hydrogen atom with one electron or a helium ion. Helium typically has two electrons. If you remove one electron, you get a helium plus one ion, which only has one electron. For lithium, if you remove two electrons, you get a lithium ion with one electron, and so on and so forth. So you got to have a system with a nucleus and one electron. Okay. All right, and then the energy for the electron in any of these orbits is given by this equation here, right? All right, and we talked about these variables, but I'll mention them again. Z is the nuclear charge, so for hydrogen that would be 1, for helium 2, for lithium 3, so on and so forth. N is the orbit, or as we'll see in a little bit, energy level, and RH is the Rydberg constant. We had this up on the last page, and the value for that is 2.18 times 10 to the negative 18 joules. All right. All right. So I mentioned that the Bohr model, the picture of the atom with all the different orbits around it, is not contained in most textbooks. What most textbooks instead have is this energy level diagram, and this uh, is the more accurate way to think about the atom. This Bohr model here in this equation here does work for a one electron atom, so hydrogen or helium plus or lithium 2 plus, so on and so forth. Okay, but those circular orbits really don't exist. So instead of thinking of orbits, the modern way to think of this is to interpret all of these, to interpret this n as different energy levels, where the first energy level is the lowest energy, second energy level is a little bit higher, third is higher than that, so on and so forth. Okay, so we could think of a transition as we were doing before. Instead of the electron moving between different orbits, we would just say the electron is moving between different energy levels. So we can have an electron in that fourth energy level. It drops down into the second energy level. And because the electron is decreasing in energy, it would emit a photon. And so we would see light coming off. And the energy carried by that photon would be equal to, the pen's not working real well, would be equal to the difference in energy between those two levels, right? We could look at absorption of a photon the same way. We have an electron in a lower energy level. I'll put it in first energy level this time. And a photon comes in. I don't know if I said photon, an electron in the lowest energy level. A photon comes in, gives this electron some energy, and when it absorbs this energy, it gets promoted or excited up into a higher energy level. Okay. All right. Now, there's an interesting thing about the way these energy levels are defined, and it has to do with this negative sign right here in the equation. These energy levels are defined in such a way that if the electron and the atom get so far apart from one another that they're no longer interacting, right? We can think of that as ionization. If you take an electron, and say you've got a hydrogen atom, and you take the electron and you move it so far away that they're not even associated with one another anymore, then you'd say that that atom has been ionized. It's lost its electron. What this model does is it defines ionization as putting the electron in an orbit that's so far away, it's essentially the n equals infinity level. And when you're in the n equals infinity level, the interaction between the nucleus and the electron is effectively nil. There's no interaction. And so we say for an atom that's been ionized, the energy is 0. We model that as the n equals infinity energy level, and the energy of that is 0. And so if the energy level up here is 0, then all of these that are slightly more stable are going to have negative energy. So that's why we have a negative sign in this equation here. So any place where the electron is associated with the atom and is sitting in one of those energy levels, the energy has got to be less than 0. So your energies are always going to be negative unless the atom is ionized, in which case the energy is going to be 0. All right, let's do a calculation for one of these transitions. All right, so this is a typical calculation you might get. What's the wavelength of the photon emitted when a hydrogen atom drops from the third energy level to the ground state? Ground state, I don't think I defined that earlier. Ground state means the lowest possible energy level. In this case, that's going to be n equals 1. Okay. So let's sketch this out, first of all, in both of these different models. In the Bohr model, we'd interpret that as having an electron here in the third energy level. It drops down into the first energy level, and as it decreases in energy, that excess energy is going to be released in the form of a photon. Right? We could think of the same process in terms of the energy level diagram. In this case, we don't have orbits anymore because, as I mentioned, the orbits aren't real. That's not actually what's going on. Atoms don't really have circular orbits. But we can say we have an electron in this third energy level, and it drops down into the first energy level. And because the energy is decreasing, that excess energy has to go somewhere, and so that excess energy is given off as a photon. And we can calculate, if we can calculate the energy of the electron in the initial state here and in the final state here, if we can calculate these two energies, then we can calculate the difference in energy, and the difference in energy is going to be the energy of the photon. Okay. All right. So let's do our calculation. Let me mention one more thing before we do the calculation. The electron is starting in this energy level, ending up in this energy level. The energy of the electron is decreasing, so we ought to find that delta E is negative. Okay? Anytime that delta E is negative, that means the energy of the electron is decreasing and a photon is going to be emitted. Okay. All right. So let's go ahead and take on this calculation, see what we get. All right. So for all of these processes, the energy of the photon is going to be the absolute value of the change in energy. Okay, change in energy might be positive or negative, but the energy of the photon is always going to be positive. So in order to get the energy of the photon, we need to get delta E. Okay? And delta E is always just going to be the final energy minus the initial energy. Okay? So if we can calculate the final energy and the initial energy, we can get delta E. All right? So let's work on that. All right? All right. We'll do the final energy first. You can do either one first. It doesn't really matter. Um, E final. Uh, the electron is dropping down into the ground state, which is the first energy level. So E final is going to be E1. And so this is negative RH. I guess I'll put these guys in here. Okay. All right. So remember our negative sign. Rydberg constant is 2.18 times 10 to the minus 18 joules. Okay. And then we need Z and N. Z, because this is a hydrogen atom, Z is the nuclear charge. So for a hydrogen atom, there's one proton. So Z is going to be 1. Okay. N is the energy level. And since this one is dropping down into the first energy level, that's also going to be a 1, right? So we've got negative 2.18 times 10 to the negative 18 joules times 1 squared divided by 1 squared. So that's just going to be negative 2.18 times 10 to the negative 18 joules. Okay, that's our final energy. Okay, all right, now let's calculate our initial energy. All right. Initial energy is going to be E3, since we started in the third energy level. So this is going to be there's our equation, and RH constant, so that's going to be the same value. Okay. And Z, this is still a hydrogen atom. So nuclear charge is 1. Okay. And we're in the third energy level. So that's going to be a 3. Okay. So this is going to be 2.18 times 10 to the negative 18 joules divided by 9. Which is going to give us negative 2.42 times 10 to the negative 19 joules. Okay. And notice negative. The energies are always going to be negative. Okay. All right. So now let's calculate our change in energy. Remember, the electron in this case is going from a higher energy level to a lower energy level. The energy of the electron is decreasing, so we should expect a negative sign for delta E. If we don't get a negative sign, then we might have a problem somewhere. We'll have to double check our work. Okay. All right. So delta E, E final minus E initial. Our final energy was negative 2.18 10 to the minus 18 joules minus our initial energy was negative 2.42 times 10 to the negative 19 joules. Okay. All right, we've got a minus, so we can just make that plus. And then when we do the math on that, we'll get negative 1.94 times 10 to the negative 18 joules. Okay. And that was negative as we expected. So that's good. That's a good sign. Okay. Ultimately, this question is asking us for the wavelength. So I've got a little bit more work to do. All right, that's our change in energy. Now let's calculate, let's look at the photon that's coming off. That's where we're going to get the wavelength from, is by looking at that photon. All right. So energy of the photon is absolute value delta E, the absolute value oop, 94, wasn't it? 94. I probably didn't need to write all of that. I probably could have just said that. Okay, so the energy of the photon is positive 1.94 times 10 to the negative 18 joules. Now we want to get the wavelength. We can't get that directly, but we can get the frequency. And then once we have the frequency, we've done a lot of calculations like that where we relate frequency and wavelength. All right. So energy of the photon is Planck's constant times the frequency. So therefore, the frequency is going to be the energy of the photon divided by Planck's constant. Okay. Our frequency is going to be 1.94 34 times 10 to the negative 18 joules divided by Planck's constant, which is 6.63 times 10 minus 34 joules times seconds. Look at our units. Our joules cancel out. And we get 2.92 times 10 to the 15 per second. Okay, so that's our frequency. That's good. We want reciprocal seconds for our frequency. And now we just got one more step to get to the wavelength. All right. So we remember from our section on light that speed of light is wavelength times frequency, and therefore wavelength is speed of light divided by the frequency. This is going to give us 3 times 10 to the 8 meters per second. Our speed of light is a constant. And our frequency we just calculated as 2.92 times 10 to the 15 reciprocal seconds. All right. And if we look at our units, we've got reciprocal seconds in the numerator and denominator. Those cancel, which gives us meters. That's good. So get 1.03 times 10 to the minus 7 meters. Okay. If the question just asks you for the wavelength, that's fine. That's correct. That is a wavelength. Typically, for atomic transitions, we usually report these in nanometers. So I'm going to go ahead and do that here. It wouldn't be incorrect if you left it in meters, but it's better to put it in nanometers. All right. Remember, there are 10. Oops, I need to put them up here. I was looking at my units and saw my units weren't going to cancel. All right. 10 to the 9th nanometers in 1 meter. Let's cancel. And this gives me 103 nanometers, which is in the UV range. All right. Okay, so that's really all we have in this Bohr model lecture. Okay. We talked about the difference between continuous spectra and line spectra. Visually, a continuous spectrum has all of the colors in it. That's the kind of spectrum that you get emitted from a hot object, which is called black body radiation. A line spectrum is when you get just specific colors, and that's what you get emitted from hot atoms, right? There are absorption spectra and emission spectra, but it's the same thing. It's going to give you a line spectrum in either case. The emission spectrum is light emitted when an electron goes from a higher energy level to a lower energy level. And an absorption spectrum is the light that's absorbed when the electron goes from a low energy level to a higher energy level. All right. You should be familiar with the Bohr model and the energy level diagram. Two different ways of describing this. In both cases, the math is the same. The only difference is the Bohr model assumes those circular orbits, which are not actually correct. The energy level diagram just replaces the idea of orbits with energy levels. Right. And you should be able to do calculations related to absorption and emission of light as electrons go from um, as they transition between different energy levels. Let's say that. All right, and we've got basically three equations here. This gives you the energy of an electron in any of those energy levels. Okay. For any transition, the change in energy is going to be the final energy minus the initial energy. And remember that if the electron goes from high energy to low energy, delta E should be negative, meaning that an electron is emitted. And if the electron goes from low energy to high energy, delta E should be positive. And in that case, a photon would have to be absorbed. Okay. Even though delta E can be positive or negative, the amount of energy carried away by the photon has got to be positive. So the energy of the photon is just the absolute value of delta E. I'll add two more equations that go back to the section on light, but maybe should have been included in here. And that is, remember that the energy of the photon is Planck's constant times the frequency. Planck's constant, of course, is 6.63 times 10 to the negative 34 joules times seconds. Okay. And remember also, if you're trying to get to the wavelength, the speed of light is wavelength times frequency. All right. And with those equations, you should be able to work your way through any of these atomic transition calculations.